So we'll be solving this CSES dynamic programming problem titled mountain range. So the problem statement goes like there are n mountains in a row, each with a specific height. You begin your hang gliding route from some mountain. You can glide from mountain A to mountain B if mountain A is taller than mountain B and all mountains between A and B. What is the maximum number of mountains you can visit on your route? Input is number of mountains and the second line is all the height of the mountains, and then output will be the maximum number of mountains that can be visited from any specific mountain. Okay. The main key points that we need to look out for in this problem is that we can glide from mountain A to mountain B. We can glide from mountain A to mountain B if mountain A is taller than mountain B and all the mountains between A and B. So this is the main condition that we need to look out for. Okay, so I have plotted this example over here in a bar graph, which will help us develop the key intuition that we require to solve this problem. I have indexed all the mountains from 1 based. So as you can see, for the index 0, there is nothing, it's an empty. So we'll use this index as a fallback. For all other values, it is 1 indexed. And here on the y-axis, it's a height for each of the mountain. So if we look closely in this bar graph, we see that from this example, if we try to understand the problem, it says that we can go from 40 to 35 and 35 to 20 or 25. But what we cannot do is go from 35 to 40. And what we also cannot do is if we have selected, if we went from 35 to 25, then we cannot go from 25 to 20 because the condition says that when we are gliding from A to B and mountain A is taller than B, then all mountains between A and B has to be smaller than A. A should be taller than mountain B and all other mountains between A and B, right? So that's the condition that needs to be met. We also cannot go from equal mountain with equal height to mountain with another equal height. Also, if we take example of this 19, we can go from 19 to 13 or 19 to 12. If we have went from 19 to 13, we cannot go from this mountain with height 13 to this mountain with height 12. Although we can, from this mountain, we can go to this mountain. It's possible because there is no other mountain present between these two which has height taller than 13. So it's possible. So if we look closely this problem and we try to identify how can we solve this. So the idea that comes into mind is why don't we use recursion to solve this problem. And if we look for recursion, then we try to see that for each of the mountain, it's possible that we are trying to find out the same solution again and again. So if you see for 40, it's possible to jump from 40 to directly 20. And if you start from 35, it's also possible to jump from 35 to 20. So for these two cases, and also if you start, yeah, for 25 it's not possible, but yeah, for 35 and 40, it's possible to jump directly onto 20. So in that case, we are solving the same problem, repeating this same subset again and again. So this hints a bit into going into the dynamic programming solution because we have identified a overlapping subproblem. Okay. But if we look at the constraints, we see that n can go from 1 to 10 to the power 5. So this tells that n square solution is not possible. Okay. So how can we solve this in n log n time? Because n log n time will definitely be acceptable and it will not give TLE. Okay. So if there is a way to identify that which one will be the out of the all the items. So if we look closely, we also come to an understanding that it is always the case that either we can glide to mountain with a smaller height either on the left or on the right, but there cannot be a path to go from here and again go back to the other side, because there is always going to be a one mountain, the previous mountain from where we have traveled to this current mountain is taller than this mountain, right? So it's not possible to go on the other side. Okay. So what we could do in this situation is always pick up the mountain which will give us the most optimal solution, which are present on the either on the left or on the right side. Okay. But we need to find that particular that optimal solution in log n time. How can we achieve that? So what if instead of thinking of going from mountain with the largest height to the one to the smaller height, what if we think of going from any of the mountain, and let's assume we have a answer for the mountain which has a height greater than the current one. Okay. So if we define the state of the dynamic programming DP solution, it goes like each of the cell will tell us maximum number of mountains that are possible to visit if we start at mountain I. And the base case, the fallback case, each DP of 0, which is 0, and indices are indexed from 1 to n. The transition, as I mentioned earlier, it will be max of left and right plus 1. And the result will be at the end, we'll get the maximum of all the DP states from 1 to n. Now, how to get this L and R? That's the main problem. And we also need to get this solution in log n for all of them. So if we see, what if we instead of traversing from, if we think of, like, let's suppose for any of the item that we are, any of the cell that we are evaluating, what if we assume that there is already an answer present for all the mountains which has height greater than the current mountain. So let's suppose if we are at 35 and we already have an answer for the uh, mountain with height 40, and we can glide from higher mountain than 40 to 40, and we have answer for that. So we can use this, right? Because the current height is smaller than 40, so it means that we can definitely add to that previous solution 1, because this a smaller mountain can also be added to the previous solution, because from the larger mountain we can come to this particular smaller mountain, right? So we keep adding from the bigger mountains, we can keep coming down to smaller ones. So what my approach would be, sort this sort all of these mountains on the basis of height of each mountain in a descending manner, and if the height of the two mountains are equal, then it doesn't matter, pick any order of the mountains. In my case, I'm taking the index with the mountain with the index larger, so it will be in descending order as well. So if we, yeah, so I'll dry run this solution as well. So what I am suggesting here is, let's suppose since we have already sorted this mountain in a descending order, so if the first mountain that needs to be processed is the mountain with height 40, so I'll take this mountain and I'll see if there is any mountain either present on the left or present on the right which is height larger than 40. Since we are at the start, there will be none, right? So the max of both, since the fallback we are considering as the height with 0, index mountain with indexed at 0, it will be 0. So max of 0 and 0 will be 0, and we add 1 into that as per our transition, right? Here is the transition says we add max of left and right, and we add 1 to it. Okay. So let me write a rough case over here. So max of 0 and 0, and we add 1 to it. So for the mountain which is indexed at 6, the answer will be 1. Now the next one to be processed is the mountain with height 35. In this, at this mountain, we check if there is any mountain that has been processed already, either on the left or on the right, which is closest to 35 and has a greater height. Okay, so on the left there is no mountain which has more height than 35, so it will fall back to 0. But on the right side we have one mountain which has been processed, because, and we check with the index, which how we identify if there is any mountain that is present on the rightmost of this particular mountain. we use this particular index. And since we are traversing each of the mountain, we are processing each of the mountain in descending manner. So we always know that if there is any index which is present on the right, it's always going to be mountain greater than the which has a height greater than the current mountain, right? So since there is one index present already, we have already processed this, so we keep storing these indexes in a tree set. So that will help me basically to find out the answer in log n time. So what I'll do is I'll find it out the index which has index greater than equals to 4 present in the tree set. If it is, since it is present, the 40 is present there. So I'll take the height answer for that, and I'll add 1 to it. So if you see, for this case, for the one with 35, on the left there is none, so we'll add it at 0. But on the right there is 1%, and answer for that is 1. So we are adding 1 into it. And index for the 35 is 4, so I'll add answer 2 as 2 for the mountain indexed at 4. The next mountain that needs to be processed is 25, right? Because that's the next one. And on the left of 5, there is one mountain present, indexed at 4, which has height greater than 25. This is the one. And on the right, there is also one present, which has height 40. So I'll take answer for both of them, and I'll take the maximum of both of them. So I'll take the 4 and 6. So you see that for the mountain indexed at 4, the answer is 2, and mountain indexed at 6, answer is 1. So we say that 2, max of 2 and 1 is 2 plus 1, and answer for that becomes 3, and index for that is 5. So we store 3 in this. So we'll use this same technique of taking maximum of both left and right. If there is none present, we'll take the fallback value, which is 0, and I'll add 1 to it. Okay, so let's proceed further for the other mountains as well. The next one that comes is 20. There is none present on left, but on the right there is one present, which is 35, and this is the rightmost, which is right closest to this 20. So I'll take the one for 35. So for 35 it is 4, on the left there is 0, so maximum of 0 and 4 is 4, and 4 plus 1 is 5. So at 1 it will be stored as, so maximum of 0 and 4 is 2, so it will be stored at 3. Next is 19. So for 19, on the left there is one mountain, which is the mountain with height 40, but on the right there is no mountain. So for 40, we see, or at index 6 there is one, answer for that is 1, but on the right there is none mountain. So for that I'll pick the fallback one, which is 0. So max of 1 and 0 is 1, and I'll add 1 to it. So answer will be 2 for the mountain with height 19, and it is indexed at 8. So let's store 2 in this. Next mountain that needs to be processed is 17, mountain with height 17. So on the left of mountain with height 17 is indexed at 3. On the left of 3 there is one mountain which is indexed at 1, and on the right of it there is one which is indexed at 4. So we take the maximum of 1 and 4, and we see that for 1 and 4 the maximum is 3, and I'll add 1 into that, so the answer will be 4 for the mountain which is indexed at 3. So let's store 4 here. Next mountain that needs to be processed is mountain with height 15. We check on the left, there is 1, and on the right there is 3. So for maximum of 1 and 3 is 4, and then so for that will be 5. Next one is 13. On the left of 13 there is 8, and on the right of 13 there is none, so it will fall back to 0. So for 8 the answer is 2, so max of 2 and 0 is 2. So I'll store at 9, 2 plus 1 which is 3. So now we have 2 of the 12. Okay, so we can pick any of them. So in my case I'm picking the one which is higher index, so I'll pick this one. I'll check if there is any mountain which is present on left and has a higher height, more height than the current one. So this is the one indexed at 9, it is present. So for this one, and there is no present in the right, so it will fall back to 0. So max of 3 and 0 is 3, and I'll add 1 to it, so it will become 4. So it makes sense, right? If we check for the indexed at 12, we see that we can definitely we can glide through 4 mountains, right? Because if we jump from 40 to 19 to 13 to 12, there are 4 mountains in total. Okay, let's process the last one. Okay, so we have last one, and we check as well if the previous height that was processed is it same as the current one. If that's the case, we don't include the previous previous mountain when checking the higher mountain with more height present on the left and right, because one condition in the question given is it has to be strictly greater to glide through. So for this particular 12 mountain with height 12, on the left there is mountain height 40, and on the right indexed at 8. So max of 6 and 8 is 2, and the answer for that will become 2 plus 1 which is 3. So answer for this current solution will be 5, maximum of the whole DP array, right? That's what it says in the result. Now let's go through the code quickly, how we are solving this. So what I'm doing is I'm maintaining an array with 2 rows. First row will hold the height itself, second row will hold the index itself, and then I'm sorting it based on the height, and the second preference will be given to index itself in a descending manner for both height and index. I'm maintaining a DP array and a tree set to hold the index of already processed mountains. That will basically help me identify which one was the mountain that has already been processed, and since we are going in a descending manner, so we already know that the items that are present in the set has more height than the current item. That will basically help me to to get the closest mountain which is more height than the current one present on the left or on the right. And I'm maintaining a buffer to filter out the mountains with the same height. Basically, whenever we encounter the different height, means that if the height previously processed mountain has a different height than the current one, we will have a updated tree set, and it contains all the mountains which has greater height than the current one. But if we encounter a mountain with the same height that we saw in the previous case when we had two mountains with a height 12, in this case the previous 12 will also be not be part of the tree set. It will be stored in a buffer. So until and unless we don't encounter mountains with different height, all the mountains, indices of all the mountains, processed mountains, will be stored in a buffer. And whenever we encounter a different height, first of all the buffer will be cleared. It will be all the mountains will be stored in the tree set, and then we can find it out the left and the right mountains index. So this is what it does. It basically find out the index of the left and the right, and if there is none present, it fallbacks to the fallback index, which is 0. And I'm taking the max of left and right and adding 1 to it. And then I'll keep on adding the current processed mountain to buffer until and unless the previously processed mountain is not same. Once it is not same, it is different. I'm clearing out the buffer, adding all of them to tree set, and then processing ahead. If both are same, the buffer will not be cleared. It will keep on adding to buffer itself. And at the end, I'm taking the max of the whole DP array. So this will give me the result. Hope you got the solution right. Thank you.